Welcome to Engineering Systems. Today, we're continuing our journey through the fascinating world of consistency patterns in distributed systems. All right, so in our previous explainers, we've already tackled some of the big ones, right? We've talked about strong consistency, that promise of perfect correctness everywhere. We've covered eventual consistency, the idea that things will sort themselves out eventually. And of course, read your writes, which just makes sure you can see your own updates. But what about all the space in between? That's exactly what we're diving into today with causal and weak consistency. Now, these models offer what you might call lighter guarantees, but don't let that fool you. Lighter doesn't mean broken. It means they're really smart, carefully engineered trade-offs designed for specific situations. So let's get into it. We're going to start with causal consistency, then we'll jump over to weak consistency, and at the end, we'll pull it all together so you can see the big picture.
First up, causal consistency. This one is all about keeping things in an order that makes sense, a logical, intuitive sequence of events. And this is absolutely critical for the user experience in a ton of applications.
So what is it exactly? Well, causal consistency promises that if one operation happens because of another, if it causally depends on it, then every single person who sees those operations will see them in the right order, cause before effect. Simple. But here's the key. Any operations that are totally unrelated, the system doesn't care about their order. It's not about forcing this one strict global order on everything. It's just about preserving those vital cause and effect links. Let's make this real with a classic example. Think about a social media feed. Alice, our project lead, posts the big announcement. This is our cause, our Operation A. It's the first domino to fall. Okay, so a few seconds later, Bob sees Alice's post, and he replies, "This is Operation B." Now, Bob's reply is causally linked to Alice's post. I mean, it literally wouldn't exist without it. His action happened because of hers. See the connection? Now, imagine a system without causal consistency. It's totally possible for some other user, maybe halfway across the world, to see Bob's congratulations message before they even see Alice's original announcement. How weird is that? It makes no sense. It just completely breaks the logic of the conversation. And that's the whole point. Causal consistency is the guarantee that stops this exact kind of bizarre, illogical ordering from ever happening. It makes sure that conversations and timelines actually feel like conversations and timelines. The benefits here are pretty obvious, right? You keep the logical flow of information intact, which gives you a way better user experience than you'd get with pure eventual consistency. And because you're not trying to enforce a strict order on everything, it's way more scalable and performs much better than strong consistency. It really is a fantastic middle ground. So let's put this on the map. Compared to eventual consistency, causal is definitely more structured. It keeps related events in line. But when you compare it to strong consistency, it's so much more flexible and faster because it just doesn't sweat the small stuff, the order of unrelated events. It's this beautiful, deliberate trade-off where you gain a ton of performance by relaxing the rules just enough, but not too much. Okay, let's totally shift gears and look at the other end of the spectrum. This is the Wild West. This is where we throw some rules out the window to prioritize raw speed and availability above almost everything else. Let's talk about weak consistency. The definition here is almost brutally simple. A system with weak consistency makes basically zero guarantees about when or in what order your updates are going to show up for other people. Updates will get there when they get there. That's it. It is hands down the most relaxed model we've got. A perfect real-world example of this is a content delivery network, a CDN. Say you upload a new hero image for your website's homepage. The server in New York might get that update instantly, but for a few seconds or even a couple of minutes, the servers in London and Tokyo could still be dishing out the old image to users in Europe and Asia. That little bit of lag, that is weak consistency in action. And for this kind of thing, it's totally acceptable. So why on earth would you choose this? One word, performance. You get incredibly high availability and the lowest latency you can possibly imagine because there's almost no coordination needed between all the different servers. When raw speed and massive scale are all that matter, think caching systems, DNS lookups, some kinds of analytics, weak consistency is absolutely the right tool for the job. But, and this is a big but, the trade-offs are huge. You get no ordering guarantees, you get no visibility guarantees. So the critical thing to understand here is that the responsibility gets pushed up to your application. Your code has to be built to handle the fact that it might be reading old, stale, or inconsistent data. It has to be okay with that.
Okay, so we've looked at these two very different models. Let's pull them back together and figure out how you'd actually choose between them and see where they fit in the grand scheme of things.
When you put them side by side, the difference is just crystal clear. Causal consistency is all about preserving those logical cause and effect relationships. You could almost call it structured looseness. Weak consistency, on the other hand, preserves nothing, except that the data will eventually get there. It's more like pragmatic looseness. Neither one is better or worse, they're just different tools for very different problems.
And this really brings us to the big picture, the consistency spectrum. As we move down the spectrum, from the rigid world of strong, through causal, then eventual, and finally landing on weak, we're making a conscious series of trade-offs. We are intentionally giving up some guarantees about immediate correctness and ordering, and in return, what do we get? We get huge wins in performance, availability, and scalability.
And that really leads us to the most important takeaway of this entire explainer. Building distributed systems isn't about always grabbing the strongest, most correct model available. Not at all. The real art is about picking the cheapest, the most performant, the most efficient model that still satisfies what your product actually means to be true. It's as much a product decision as it is an engineering one.
So how do real live production systems actually mix and match all of these different models? Well, that's exactly what we're going to cover in our next explainer. Thanks so much for watching. If you learned something new today, do me a favor and hit that like button. And of course, make sure you're subscribed to the Engineering Systems series for more deep dives into the concepts that power our digital world. I'll see you in the next one.